All right, guys. So this is technically what would have been section 10.8. I mean, it's not a section that we really have to cover. All it does, well, it provides us with a summary of the tests, and what it does is just throw up a bunch of random exercises so you can choose the most suitable test to determine the convergence or divergence of the series. Well, in fact, I got this table from a different textbook. I can't remember which one is, if it's Larson's or Stewart. And well, actually, the tests that we have here are not in the order that we covered throughout the class, right? Well, I think we started with the end term. No, we didn't start with that one. I think we did the telescoping first and then the geometrics test. All right. Well, so this table right here. Well, number one, the first column gives us the names of the different tests, the end term test, geometric, telescoping. All of them are here. All right. And the second column is how the series looks like, so we can compare it with, or yes, actually compare it with with the best method or the best type of series to do the test. Well, the third and fourth condition give the conditions for convergence and divergence respectively. For example, and it's important to review all. Let's have a look at all of them. Okay, so for the end term test, recall that the end term test doesn't tell us anything about the convergence of the series. It only tells us about the divergence of the series whenever the limit is different than 0. All right, and that could be 1, 5, square root of 7, infinite, or infinity, or that is the limit it's DNE. So that's when the series divergence. All right, so it doesn't tell us anything about convergence. And well, this idea right here is very well tied with the comment that we have on the fifth column, which is some comments about the different tests. And that's that when we have a limit equal to 0, then the test is inconclusive, and therefore, we have to find a different way, a different test. The geometric series, it looks like sigma equals 0 to infinity, a r to the n. Recall, very important, that the starting index for the geometric series is n equals to 0. And we covered a few examples in our lectures in which the series was not starting at 0. Some of them started at 1, some of them I believe started at 2, and in this case, we needed to do what we call the shifting the index, right? And that's something that's going to be on the test for sure. I'm going to give you something on the exam in which you will have to do some shifting of the indices. So you might want to write that down. So I think that's a good giveaway for the test, right? Just something you would be expecting to do. All right, so converges when r is a number, when the absolute value of r, the number that gets raised to the n power, is a fraction between 0 and 1, and diverges otherwise when r, the common ratio, it's either equal to 1 or greater than 1. And as a comment, this is one of the series for which we can find the infinite sum along with the telescoping series. Recall that there's only 2 out of the 10 tests for which we can use to compute the infinite sum. And yes, you would expect to see one of each for which you will use the telescoping, and another one for which you will use the geometric series with the corresponding shifting. So be aware of that. All right. Telescoping series. The textbook, and if you look at the viewing example on my MATLAB, first it asks you to compute, or rather expand some terms, and then come up with a limit expression, compute the limit. But all we did in our class is just cancel the terms. Cancel terms, and the infinite sum will be whatever term survives the cancellations, right? And yes, here the limit is L, and the sum, well, it's whatever. Well, in the case that the limit is something other than 0, but most of the times we get something for which the limit would be 0, and that's just whatever terms just survive. P-series, well, I think that's one of the easiest ones, but I mean, for the P-series, I'm not going to give you something like, oh, sigma n equals 2 to infinity or 1 over n squared. I mean, you will be just telling me that P is greater than 1, so converges. I mean, how many points could I give you about it? I mean, like 2 points, maybe 1 point, I don't. But rather, I would give you something more elaborate. For example, a series for which we would use either a direct or a limit comparison test to relate that given series with something that looks like a P-series or a geometric series, or something like the alternating series test, in which we first do the two conditions. We're going to talk about that one soon, and then you take the absolute value of the series and come up with something new, and you may use again a direct comparison and with another P-series perhaps. So actually, I mean, the P-series is only a very tiny yet powerful tool to check the divergence or convergence of more composite or more elaborate series. Okay, which one is next? Oh yeah, the next one, alternating series test, of course. The condition, well, they look like this. They have an alternating factor, some -1 to the n power, or -1 to the n plus 1 or n minus 1, which produce this bouncing between positive and negative, and then some algebraic rule A sub n in general. And well, the two conditions for convergence is that the limit of the expression without the alternating factor is 0, and that we have this non-increasing condition, all right? And then from here, if one or both conditions fail to be satisfied, well, we're done, and the series diverges. Well, comment, see the flow chart below, and below the table, I copied and pasted the same diagram flux I gave you on the lecture notes. The one that, and you might want to write it down on your sheet of notes as it is, or if you want to annotate more stuff, of course. And again, first thing we do, find the limit. If the limit is 0, well, then we're good. Second condition, non-increasing, then we're good. Okay, if both conditions are satisfied, for now converges. Furthermore, we take the absolute value of the series to check for absolute convergence or conditional convergence. And that happens when the new problem that we produce after taking the absolute values, that new series may converge or diverge. So at this point, what we do is forget about the original alternating series and concentrate on that new series. If that new series converges, well, the series converges absolutely, but otherwise, if that new problem series diverges otherwise, well, converges conditionally, all right? And again, if one of these two conditions fails, well, just diverges and we're done. Typically, do the limit first. If the limit is 0, then do the non-increasing. If the limit is not equal to 0, diverges, because, well, basically, and here is the connection with the other test. Here, if you get a limit that is not equal to 0, isn't that really the n-term test for divergence? So that's the connection between the two tests right here. Okay, so that's the alternating series test. Then the integral test. And yes, I mean, so we were talking about, yes, the integral test. So for the integral test, well, so when you look at the different given infinite series, most of the times they have the look of some f of x that looks integrable. Yes, of course, I agree with that. However, we cannot just use the integral test like that. Number one, we need to make sure, number one, that the function that represents the series is continuous, is positive, and most importantly is decreasing. If one of these three conditions fails to be met, then you cannot use the integral test. And this is just going to take us back to improper integrals. So we find the integral as long as the three conditions are satisfied. The integral converges, the series converges. The integral diverges, the series diverges, all right? And also, the value of the integral is not equal to the value of the infinite series. So that's something that you might want to keep in mind. So we're just determining convergence or divergence of the series. Okay, so for the root or the ratio test, the conditions are exactly the same. If the limit is less than 1, we have convergence. The limit greater than 1, we have divergence. But when the limit is it's exactly equal to 1, test is inconclusive. And well, direct comparison and limit comparison, well, in some cases, direct comparison is very quick because all we do is either show that tiny is less than small or huge greater than big. And sometimes, put the expressions together, it should be clear. As long as you say, just put a check mark. You don't have to solve an inequality as long as you justify that, for example, for tiny less than small, you have a larger degree or a larger order in the denominator of the left-hand side, greater and greater on the right-hand side. Of course, as long as the inequalities make sense, check mark. That's all the argument I need, or that is needed.
It's easier than doing the limit comparison. Like if it fails, the direct comparison, then you would lose.
Yes. Yeah, but now we recall that some things can go wrong with the direct comparison, for example, and I think I did one example like that, and let me just touch base real quick on that one. Nope. Square root of n plus 1, for example. Well, this one looks like n equals 0 to infinity, 1 over square root of n, which is over n to the 1/2, which is p equals to 1/2. So this is a divergent p series, right? So for divergence, we need to make sure that huge is greater than or equal to big. But in this case, well, the huge is the original problem, and the big one is just 1 over the square root of n. But is this inequality true? No, right? So in this case, well, direct comparison failed, so we need to go with limit comparison, all right? That's our plan B. Again, those are the situations that can go wrong when it comes to using the comparison test. And
don't just assume that the tiny is less.
Exactly. So just because it looks like right now, if otherwise I had the series n equals 0 to infinity, square root of n, but what about minus 1 in this case? That minus 1 is going to make the quantity smaller, giving us a larger value. And yes, in this case, huge greater than big. That should work in this case. All right. And what else? So let's see. I think this pretty much summarizes the whole chapter 10. All about the different tests and all that. So really, this is really not an official section. It's more like an optional section but in this case, all we do is just go over the key points for the different tests for convergence and divergence.